Hey everybody, welcome to this video. Special thanks out to Mrs. B for letting me borrow her computer. This video is going to focus on water. And by focus, these are going to be some of the questions we're going to address. Why is water so different from a molecular sense? Why are hydrogen bonds so common in water? And why are they important? And what properties of water are present because of the way water is put together? And then finally, kind of from an A&P perspective, why is water so key to homeostasis? First, let's address this question. Well, let me ask you this. Name me a living thing that does not require water. You can't do it because every living thing requires at least some water. And water has many uses that we'll get to in a second. But why water? Water is different from a molecular sense because it's going to have so many of these bonds that we mentioned in class, these hydrogen bonds that connect water molecules together. You see hydrogen bonds here. This is really a weak attraction between this water molecule and this one. Again, just to make sure that we're all on the same page, this little white thing here is a hydrogen. So is this one. And then this, of course, represents oxygen. We can write water like this. And so we tend to see it written with the structure like this. And you'll often see a single line that connects the oxygen and the hydrogen. And these represents a bond, a covalent bond. Another way of writing this is we can have the hydrogen here and the hydrogen here, and we can have the oxygen. And instead of doing that shared bond that you're seeing there, we can draw in the electrons. So let me do that. The electrons that are shared, there's a pair of electrons that are shared between hydrogen and oxygen in this one, but the electrons are not going to be here. They're going to be right there. They're going to be very close to oxygen, and the pair that's shared over here, same thing, going to be very close to oxygen. They are shared, but they're not shared equally. So what do we call that kind of covalent bond? That is a polar covalent bond. So what you're seeing in all these cases is, again, they're not showing the electrons, but you have an oxygen and a hydrogen and a hydrogen. But within that, there's this mini tug of war going on so that oxygen ends up with electrons next to it. So what, who cares? The problem or the issue or the cool thing, depending on your perspective, is oxygen takes on a slight negative charge. You will see, and I'm going to have a very hard time drawing it with the mouse, but you're going to see something like this, like a little delta with a plus, or a little delta with a minus. That delta, that's what that thing is right there, that delta represents, it means slight. So oxygen has a slightly negative charge because the electrons are next to it. Because you pull negative away from the hydrogen, hydrogen has a slight positive charge. And because I have a negative piece and a positive piece and a negative piece and a positive piece and a negative piece and a positive piece, I'm going to have all these weak attractions between a negatively charged oxygen because it's so electronegative, such a good electron puller, and positive hydrogens because they're not very good pullers. I'm going to have all these little mini magnets, if you will, in a glass of water, and it causes water molecules to really stick together. And when you hear this term that water is molecularly sticky, that sounds stupid because water doesn't feel sticky. No, but water is sticking together, the water molecules, at the most basic level. Okay, well, why is that important? Well, just showing you an example of lots of hydrogen bonds here. So why is it important? If water is going to stick together with all these tight connections, some properties for water are going to emerge that are very important. For example, water is very good at storing heat. If you think about what heat is really just the amount of movement of molecules. It takes a lot of, you see there, hydrogen bonds require considerable heat before they break. If you have all of these things stuck together and you try to heat up water, it takes a long time and a lot of energy before you get these things to break apart. Water tends to stick together. Water also is not going to change temperature then very quickly. That is important from a heat storage capacity. Think about, again, a body of water like a lake. It doesn't get cold very quickly. It's going to cool down slowly. It's going to heat up slowly, therefore minimizing big changes in water temperature. Ice. We're not going to talk much about ice from an A&P perspective, but water is a little different because when it gets cold enough, it actually doesn't get really dense. It kind of braces itself with these bonds and water floats. Again, it's more of an ecological property. We're not going to focus too much on it here. Water has high heat of vaporization. For water to go from a liquid to a gas requires a lot of heat. And we expressed this in class with discussing how hard it is to boil water. It takes a lot of energy and a little bit of time to make water break because it's being held together by all those bonds. Water is very cohesive. Hydrogen bonds hold water together, and water has high polarity. That is, it has a positive and a negative end. So if you put that with ion molecules, then it's going to be easy for water to help break them down, because for every positive sodium and negative chlorine, there's going to be a negative oxygen and a positive hydrogen kind of pulling it apart, because they're like little mini magnets in solution. So here's just an example of how cohesive water is. Just a great picture. And you see how water kind of sticks together. Water sticks together in ways which makes it possible, for example, for a water strider to walk across a sheet of water. But let's take let's look at this again from an A&P perspective and talk about it from why is water so important for our bodies. We need water for chemical and metabolic reactions. That is, water is going to be a special ingredient for us to use in some reactions, and it's also going to be the medium, that is, the substance in which reactions occur. Water is also going to be important, again, as a transport medium. It's going to be what's called a universal solvent. Think about blood. Blood is mostly water. Why do we have so much water making up our blood? Because lots of things can travel in it. Based on water's properties, many things can travel in water and therefore be moved from one part of the body to another. Water assists, of course, in the removal of waste. When we produce urine, we actually get rid of that waste with a fair amount of water. If we didn't have that water, we'd have to spend a lot more energy to make that waste safe to be in our bodies, and we don't want to do that. As we've mentioned, water is quite important for temperature regulation. The fact that you are 2/3 or more of water means you're not going to change temperature very quickly, and that's good. If you go outside on a hot day, you don't want to have all your water begin to boil or to have all your water freeze when it's cold. And think about how water serves as a cushion. You have a lot of water in and around your organs and around your tissues, which helps protect us from physical trauma. So, in short, water is really important to homeostasis. Remember what homeostasis is. It is not that our conditions never change. It's that we tend to keep our internal conditions relatively constant. Because of water's properties, water doesn't change very much. Water kind of protects us from these highs and lows, these big temperature swings, and gives us the chemical substance in which most of our reactions occur. So water is critical for us to live. In the next video, we'll look at water kind of from a different perspective as we talk about acids and bases. Thank you very much for watching this video.